Okay. Let's see. Yep. See 3 of you. 4. Great. So going to share my iPad. Here it is. Okay, let's find which one I used. Yep. Okay, so you probably know this really well by now, but if you want to temporarily unmute yourself, you just hold space. So when you hold space, you'll get unmuted, and then you release space and you get muted again. Okay, so I'm going to open chat. So important thing is that in my previous class, the internet wasn't always working so well. It was more or less fine, but then I disappeared a couple of times. So, which actually not fine. So if you see that my voice is freezing or the picture is freezing, let me know in chat. I'll probably realize this soon enough because I also see my iPad picture, and if it's freezing for everybody, it's also freezing for me. But here is the chat. And if you notice that something goes wrong, you can type it in chat, or you can unmute yourself and thank you. You can unmute yourself and ask a question.
I like your background.
Thank you. Yeah, it's like a vacation. Okay. 1 second. Yep. I was actually seriously thinking about going to Hawaii for this entire time because the tickets are relatively cheap. But I was afraid of getting stuck there forever. Okay, so let's start integrating. So we'll just do some more applications of, well, some more residues, and here we'll have one general fact about how this integral, so we'll always integrate over this contour with semicircle. And last time in YouTube, I told you that you always need to prove that this limit is 0 by hand. This time we'll have some general fact, but the price we pay for the general fact is that it's not really easy to prove. So I'll skip most of the proof and you'll just have to believe me. So the book calls it, so it's section 80, the book calls it improper integrals from Fourier analysis. I will call it trigonometric integrals. For obvious reasons, they will have trig functions. And we'll start with an example right away. We'll integrate this function. So we will draw our contour again, the same CR. And now, so a general fact is that cosine and sine are kind of bad, although even when we plug the z, they remain analytic, but it's typically better to replace cosine of whatever, of 3x in this case, not with, so the like simple way would be cosine of 3z, but this is wrong This is typically a wrong approach. We'll instead replace it with e to the I times 3z. So this I will help us. And what do we get then? Well, first of all, we know that cosine of 3x is still very much related to e to the I times 3z. But second of all, an important thing that we know is that, so CR consists of two parts. So CR consists of this part and this part. And this part goes along the x-axis. Okay, so x-axis are here. So if we integrate over this blue part, our f of z, we know that the parameterization of the blue part is just z is equal to t, or z is equal to x, from minus r to r. And what's f of x dx? Well, now we just need to plug the complex variable, the real variable instead of the complex variable. And this will be integral of cosine of 3x, the one we need, over x squared plus 1 square, plus I times the integral of sine of 3x. So I'm writing e to the 3xi as cosine of 3x plus I sine of 3x from minus r to r, from minus r to r. So it means that the integral that we need, this one, okay, it mildly freezes. So this integral is just the real part of this integral. And this integral will compute in terms of the integral over the whole closed contour, which we do with residues, and the integral over this orange part of CR, which will hopefully go to 0. So at some point I'll need to take real part, but that's not a hard task. So, well, I at least hopefully somewhat convinced you that this is not a suicidal replacement. So when we did e to the I3z instead of cosine of 3x, it wasn't a failure, at least. So why does it help us? So I'll give a very sketchy why does e to the 3xi help? 3zi, sorry, 3zi. I'll give a very sketchy reason. The reason is when z is equal to x plus iy, and y is huge, we have e to the 3zi is equal to e to the 3xi times e to the minus 3y. Okay, so I take z and I multiply it by I. So I times iy is minus y. So I have minus 3y. And this helps with an estimate, with our estimates on this part of the contour. So see, this contour, well, it has these parts where y is not so huge, but then it has this hill where y is huge, and at least on the hill we get some really decent exponential decay. So this we will eventually summarize in what's called Jordan lemma, but before we do Jordan lemma, we'll do this example. This example is easy enough to go well. Anyway. Okay, So let's go back to our example. So we have this f of z e to the 3i times z divided by z square plus 1 square. We're integrating it over this contour CR. And this contour has only one pole. So f has two poles, z equal to plus or minus I. So these are poles of multiplicity 2. But minus I is not inside the contour. So only I is I somewhere here. And so we know that the integral of f of z dz over this contour is equal to 2 pi I times the residue of f at I. So let's find this residue. So I'll rewrite f of z like this. So I'll factor the denominator. So z square plus 1 is z minus I times z plus I. And I need to square both because z square, we have z square plus 1 squared. So we square both. And I'm interested in the residue at I. So let's write it like this. And we'll call this phi of z. Call this phi of z. And now we have f of z is equal to phi of z divided by z minus I square. And now I'll go many pages back with a big hope that my screen will not freeze. So before the application of the residues, before this p divided by q, before everything, yes, we did this phi right here, for example. So here it is. Well, this was actually a simple pole, but somewhere before that, yeah, so see, yeah, way before that, so here it is. We figured out that if we have a pole of multiplicity n, then we need to take n minus 1 derivatives of phi. So you saw how many pages back I went. I'm now on page 6 out of 23. So you can also go this many pages back, find this statement, and the point of the statement is that the residue of f at I is phi prime of I divided by 1 factorial. Well, 1 factorial is 1, so we just get phi prime of 1 of I. And my big yawn is because I'll now need to differentiate phi. I was avoiding this. I was always telling you that if our life depended on taking this derivative, we'd be able to do this. Well, now my life still doesn't depend on it, but I have to do it. So my phi is this. Let's differentiate it. So 3i, I'm going to use the quotient rule, obviously. Like this. And now I need to plug z equal to I. So I got 3i times e to the minus 3 times 2i squared minus 2 times 2i times e to the minus 3 divided by 2i to the 4th power. All right, so 2i squared is minus 4. So this is minus 4. Okay, minus 4 times 3 is minus 12. And here I got -4. Okay, and 2i to the fourth is just 16. So -12 minus 4 is -16. 16 cancels out, and I got -i times e to the -3. Okay, I'm actually going to check with the book. Yes, that's correct. That's correct. So that's the residue of f at I. It's -i times e to the -3. And so this implies that the integral of f of z dz over cr is 2 pi I times -i e to the -3. Okay, I times I is -1. -1 kills this minus, so we got 2 pi e to the -3. So that's the integral of f over cr. Okay, now we know what? We know that the integral of f of z dz over cr, as always, is equal to the integral over this horizontal part plus the integral over the round part. And this is the integral from -r to r f of x dx plus this. So my next step is to show that this second term goes to 0, as always. So this second term should always go to 0 as r goes to infinity. And there's only one way we can do it, that is, we estimate. Okay. Everyone's happy, hopefully. So how do we estimate? Well, we need to, we estimate as always. F of z dz is less or equal than the max of absolute value of f times the length of this path. The length of this path is 2 pi r. So we need a decent estimate for the maximum of f. Okay, so what's f of z? F of z is this. And now we should be extremely careful, because we're very used to the fact that this is 1, but it is not. This is 1 only if z is a real number. But z is a complex number, so this is not 1. But I'll very soon show that it's smaller than 1. So why is it smaller than 1? Because if z is equal to x plus iy, sorry, I put my iPad on the table, so for a while you'll see my terrible hair. So z is x plus iy, means that e to the 3iz, we had this before, is 3 to the e to the 3ix times e to the -3y. So the absolute value of this is the absolute value of e to the 3ix times the absolute value of e to the -3y. And this is 1. So x is real here, so e to the I times whatever real number, in this case 3x, always has absolute value 1. And this is not 1. But fortunately for us, it's less or equal to 1. Why is that? Because we're integrating over the contour which is in the upper half plane. Okay, and in the upper half plane, y is non-negative. And if we take e to the power -3 times non-negative, we always get less or equal than 1. So e to the 3iz in the absolute value is less or equal than 1. Less or equal to 1. And the rest is what we've done before. So z squared plus 1 absolute value is bigger than z squared minus 1, which is r squared minus 1. And so absolute value of f of z is less or equal to 1 divided by r squared minus 1 square, which is great because now this integral is less or equal than 2 pi r times 1 over r square minus 1 square, and the denominator kills the numerator, so r square minus 1 square is like of the order of r to the 4th, so this definitely goes to 0 as r goes to infinity. Okay, so now what do we have in the limit? So in the limit we have the following, that okay, let me remind you what do we have without the limit. So on one hand we got that this is equal to pi times e to the minus 3, right? 2 pi e to the minus 3. 2 pi e to the minus 3. Oops. On the other hand, it is equal to the integral from minus r to r of f of x dx plus the integral over this f of z dz. And let's recall what is this first term. So f involves the exponential. So in fact here we have cosine, and this is what we want, plus I times sine, which is what we don't want. And this term is still here. Before we pass the limit, it will be here. Now, here's an exercise for all of you. In fact, I don't really need it, but in fact, this second integral is always equal to 0. That's because sine of x is an odd function, and the denominator is an even function. So we're integrating an odd function from minus r to r, and we must get 0. But in fact, I don't need it, because I'll first pass to the limit. So let's take the limit as r goes to infinity. Well, this left-hand side didn't change at all. And in the right-hand side, I'll just get this. With or without principal value doesn't really matter, because this integral converges nicely. And this integral also converges nicely. So plus 0, because this goes to 0 as r goes to infinity. Okay, and now I have the integral that I want plus I times the integral that I don't want. But this is purely real, and this is purely imaginary. So I can take, so this is purely imaginary if we include the I. So now you can just take the real part of the left-hand side and the right-hand side. So, well, left-hand side is purely real. Actually, I don't need the real part so much. But even if this left-hand side had plus I times something, I would just take real parts, and I would say that real part of the left-hand side is equal to the real part of the right-hand side. And it's slightly more general than showing that the second integral is 0. So take the real parts, and we get this is equal to this. In fact, we could also take the imaginary parts and see that the second integral is 0. So there is no need to prove it by hand, in fact. And so that's the answer. So all these problems are relatively long. They all follow the same pattern. And after I state this Jordan lemma, oh yeah, I have a question. I'll answer the question in a moment. So after I state the Jordan lemma, it will be slightly faster. Okay, so is your curve oppositely oriented? Yes, yes, absolutely. Goes here. Agreed. Here it was correct. Here it's correct. Yes, thank you. Good catch. Here I drew two arrows in the opposite direction. I should bring the chat to some more visible place. Sorry, I'm trying to keep the textbook on the screen, my iPad screen on the screen, and the chat. So, yep, okay. Okay, so what is the Jordan lemma? So the Jordan lemma says that in fact, this e to the iz helps a lot. So the Jordan's lemma says the following. I'll write it and draw the picture. So assume f is analytic outside of the circle like this. So this is not supposed to be a variable circle. It just says that f has all its problems inside some fixed circle, which it always does. For example, this f had a problem at plus or minus I, so outside of the circle of radius 2020, for example, this f was nice and analytic. Okay, so we assume this. So outside of, I can also add, we typically won't need it, but I can also add that I'm interested only in the upper half plane. Okay, so then assume also that on our favorite part of CR, we have an estimate something like this, M of R. So our estimate is different for different radii. It actually should become better. And this M of R goes to 0 as R goes to infinity. Then no, sorry, not over CR. Then this integral but now not f of z. Now we'll have f of z times e to the I a z dz goes to 0 as z goes to infinity. Who is a? A is any, let's see, a is any positive number where a is bigger than 0. Okay, so too many lines in this lemma. What does this lemma tell us? Well, let me explain on the example of this function. So having such an estimate, having an estimate f is less than m sub r, when m sub r goes to infinity is not enough. It's not enough for like a straightforward approach, because we're multiplying our estimate by 2 pi r, which becomes huge. So here we needed something more. we didn't need that this only goes to 0. So see this second box, it does go to 0 as r goes to infinity, but we needed more. We needed that it goes to 0 faster than this goes to infinity. So if our estimate is something like this, let's say 1 over square root of r. That's an r. Then our straightforward approach, what was the straightforward approach? The straightforward approach was to say that this is less or equal to 1. This is what I did. Sorry for going back and forth. This is what I did right over here. Saying that this is less than 1 will result in the following estimate. So I have the length of my contour, which is 2 pi r, times 1 over square roots of r. Well, this is huge. So that's a very bad estimate. So if I do this, I failed. What I need to do is to effectively use this term, because this term actually also becomes small, because we saw that this term involves e to the minus y, and y is potentially big, so e to the minus y is potentially very small and helps. So this lemma is stronger than what we did next, but unfortunately it involves this. So if we're integrating a function without this exponential, then we cannot use the Jordan's lemma. If we're integrating a function with this exponential, then we can use Jordan's lemma, and we still need. Yeah, Audrey, I'll answer in a moment. So we still need this estimate, but we don't need it to be so strong. What's the relation between r0 and r? Very good question. So r0 is fixed, and r goes to infinity. So r is getting bigger and bigger than r0. So let me give you an example. Let's discuss the same function again. So function from the previous example. E to the 3iz divided by z square plus 1 square. Okay, that's actually bad notation. Let me temporarily call it g of z. So g of z is equal to 1 over z square plus 1 square times e to the 3iz. So first of all, what is our f? Our f is everything except for the exponential. So now our f is this. Now, back to your question. So for r0, so r0 is something fixed. So to figure out r0, we just need to find a circle big enough outside of which f is analytic. So we need to just fix r0 such that f is analytic outside of the circle of radius r0. So we can fix r0 from the very beginning. For example, r0 can be equal to 10. 10 is good enough, because if we have a circle of radius 10, then all the problems that f has are inside the circle. So if r0 is 10, and here's one pole, here's another pole, and besides these poles, f doesn't have any problems. So r is fixed, so we fix it forever. r0 is fixed. Now r is something that's going to change. So r will be what defines this contour CR. So R0 compared to R is something teeny tiny. That's R0, that's R, and R goes to infinity. So R0 is fixed forever. R is not fixed and goes to infinity. So that's the difference between R0 and R. So I'm using the book's notation because I expect you to read the book at some point. If I wanted to invent my own notation, I would use different letters. Like instead of R0, I would use a little r to emphasize that R0 does become bigger. So we will see some more examples, and maybe it will become more clear. Oh yeah, so I kind of need to prove this lemma. So let me give you a very rough idea. So sketch of the proof. So if we're integrating over this, and what I forgot to say is that I want y to be non-negative. So we're integrating over only this part of the contour, sorry, as we always do. Well, we just parameterize the circle, okay? We just parameterize the circle. So it means that we have f of theta is equal to r e to the I theta, and because we're only on the semicircle, it means that theta is from pi to 0. So we don't go all the way to 2 pi, we go only to pi. So now we need to integrate from 0 to pi f of gamma, f of gamma of theta times e to the I r e to the I theta. Then we need gamma prime, which is I r e to the I r theta. No, sorry, r e to the just I theta, just I theta, d theta. And this thing, this second thing, let's also write it. So with f of gamma of theta, I really cannot do anything. Okay, I don't know what's my f. My f is something general, so I cannot do anything with it. Now here I'll have I r cosine of theta, and then I'll have minus r sine of theta. And then I have this. Okay, now I'm going to cross out everything that won't help me. So this won't help me because the absolute value of this thing is always 1. Always 1, because r is a real number and cosine of theta is a real number. This won't help me because its absolute value is 1. I'm not saying that it cancels out. I'm saying that if I take the absolute value, it will disappear. This won't help me. F will help me, but because f is general, so there's only one single thing we know about f. And this one single thing is that it's less or equal than m sub r on this semicircle. So let's use this, and what is left after we factor out m sub r is this. Now, there are two cases. One case is that I can prove that this integral is bounded. If I prove that this integral is bounded by some universal constant, in fact, it is bounded, oh sorry, it's not minus pi to pi, it's from 0 to pi. So if it's bounded by some number, no matter what r is, then I win, because this is bounded and this goes to 0 by assumption. Now, second case, I cannot prove that this integral is bounded. Then I lose. So in fact, it is bounded. And the book works kind of hard to prove it, and I won't. But in fact, it's less or equal than pi. And then we win. Because let's look back, we know that the integral over this curve is equal to this. Then just imagine putting the absolute values before the integral. Then we'll write less or equal and bring the absolute value inside the integral. This disappears, this disappears, this disappears. This is estimated by m sub r. So we get that we're less than this. And this is less or equal than m sub r times pi. And this goes to 0. So that's exactly what we want. So theoretically, myself and the book could torture you a little bit and make you repeat this step in every problem. But Jordan, fortunately for all of us, realized that this step has a very general setting. And so we can now just refer to Jordan's lemma and be happy. So I encourage you to look in the book on page 273 for the proof of this estimate. It's not so hard. I just think that you all are very tired of me estimating, so I'll skip this. Okay, let's do an example. So let's integrate this. And by the way, Jordan's lemma is what justifies replacing sine and cosine with the exponential instead of replacing sine of x with sine of z. Because Jordan lemma will not be true for sine of z. It's true only for e to the iz. Okay, so we need this integral. And the pattern is to replace sine of z with sine of x with e to the iz. In fact, you know what? I'll be a bad guy, erase this all and write it with an x. And now what we need is the imaginary part of this integral. Okay, because e to the ix is cosine plus I times sine. And to get the sine, so we need the sine, here it is. It means that we only need the imaginary part of this integral. Well, but in any case, we now introduce our contour CR. So this is CR. Let's try to orient it correctly. And we'll integrate z e to the iz divided by z squared plus 2z plus 2 dz. Okay, and we know that this is 2 pi I times the residues. So who are the residues? Well, what are the poles? So for the poles, we need to solve this, and we did it last time on YouTube. So z is -1 plus or minus I. So -1 minus I is here. It doesn't help us. -1 plus I is here, and it does. So it's 2 pi I times the residue at -1 plus I. Of what? Of z e to the iz divided by z squared plus 2z plus 2. Now this is not hard to find because -1 plus I is a pole of multiplicity 1. So this is just 2 pi I times, so we did a similar thing last time. So we need to plug -1 plus I here, and then we need to differentiate this and plug -1 plus I. Okay, so I'll just write it like this. Plus 2 with the substitution z equal to -1 plus I. Let's do it carefully. So it's 2 pi I times -1 plus I, sorry. Where is my eraser tool? It is -1 plus I. So -1 plus I e to the I times -1 plus I And here I'll have 2 to the minus 1 plus I plus 2. So it's what? Yeah. It's 2 pi I. I have minus 1 plus I here times e to the minus 1 minus I here. And here I'll have minus 2 plus 2i plus 2. So minus 2 cancels out, and I'm left with 2i. So 2i and 2i cancels out, and I end up with this terrible answer. Okay, we will remember this because at the end of the day, we'll need to take the imaginary part. Oops, am I freezing? I am, but not badly. So I'll need to take the imaginary part, so at the end of the day, we'll need the imaginary part of this terrible thing. And I won't have time today to do it, so it will be an exercise, and next time we'll do another example. I just want to show you the Jordan's lemma. Okay, so this integral over CR is equal to the integral over this, which is what we need, plus the integral over this. And for the second one, it's exactly the integral over this semicircle of x of z, divided by z squared plus 2z plus 2 times e to the I z dz. And the Jordan lemma suggests that we only need to estimate z divided by z squared plus 2z plus 2. And this is our regular thing. So I'll do it quickly because this is on YouTube already. We already have this example, and we know that it's bigger than r squared minus 2r minus 2. And so this is therefore less or equal than r divided by r squared minus 2r minus 2. So this will be my m sub r, and this goes to 0. Okay, it goes to 0 slowly, not fast enough for our brute force method, because in our brute force method, we would multiply this by 2 pi r, and the powers will match, r squared on the top and r squared on the bottom. So our brute force method would fail. But our Jordan lemma method doesn't fail, because for the Jordan lemma, we only need this to go to 0. And this is because we already have this friend. So by the Jordan lemma, this integral goes to 0 as r goes to infinity. And so what we eventually get, okay, I'll write it and I'll stop, that this 2 pi I times the residue, so it, okay, forgot it again, pi times minus 1, pi times minus 1 plus I times e to the power minus 1 minus I is equal to the integral from minus infinity to infinity. I passed to the limit again. X e to the ix divided by x squared, plus 2x plus 2. So the integral that we wanted, x sine of x divided by x squared dx plus 2x plus 2 dx, is equal to the imaginary part of this thing. So the last step in this example that I'll leave as a small exercise is to actually compute the imaginary part. So what's the answer? The answer will eventually be pi over e times sine of 1 plus cosine of 1. So I encourage all of you to verify this. So that's a funny answer. It involves pi's, it involves a pi, an e, a sine, and a cosine. Okay, so we'll stop here, and I'll upload this lecture on YouTube as well, so you'll be able to rewatch it. I'm not sure I want to upload my notes anywhere because I scrabble a lot. And I'll see you on Wednesday, so please don't hesitate to ask questions on Canvas. I already answered to, yep. Last night said they would mention, oh, yeah, damn it. I should have. I just want to do the example so badly. Yeah, so let's do the homework on Wednesday. So we will discuss the problems in the homework that you turned in on Friday. And then, so I will do this first thing. And then we'll continue with the examples. Yep, sorry. What email we're supposed to send the homework to? Oh, any email. Yes, I got yours. Any of my emails you can find on the internet should work. In particular, you can just reply to any of my Canvas, to any of my emails through Canvas. So if you take any of the emails you got from me and just reply, I'll get your response. Yeah, but I think you sent me 2 copies and both worked, both arrived. Yeah, so let's discuss the homework on Wednesday. This was a very good reminder. Sorry to do it today. Yeah. Let's see. Do we have another homework? No, not yet. So due this Friday? No. Again, not yet. Probably will be due next Monday. Did I get yours? March 27th. Yeah. Yes. Yeah. Enrique. Yeah, I got yours. Yeah, you were the one who replied through Canvas. Yes, I said something about the homework being extra credit. This is true. So this one won't be. I said that all the homework after this one. But the rest, yes, the rest will be mainly extra credit. Maybe I like assign 1 or 2 mandatory problems, but except them, they'll be extra credit. I just think that because the overall quality of lectures and office hours decreased very much, I don't want to force you too much to do lots of homework. But on the other hand, because the quality decreased and because we covered most of the super important material, I can take this chance to give you some extra credit, which I promised not to do, but now I can. And yeah, so I can give you some extra credit to improve your score, which I think everyone will appreciate. So yeah, so let's discuss the homework on Wednesday. The new homework will be mainly extra credit, and I got all of your homeworks, hopefully, so that's fine. Okay, so I'll create another Zoom meeting for Wednesday, and I'll see you then.